Hello, welcome back to Geography 300 video series, Geographical Analysis for WVU. In the previous video, and really both previous videos, we were looking at building up towards making inference about relationships between two variables using linear regression. And we saw how we can look at p-values for, say, either the r squared or the coefficient to understand the effect or the relationship between those two variables. Now, this video, looking at pitfalls, is telling you where things can kind of break down. And the first kind of ways that this inference process can break down is that it's actually making some assumptions about the data that may or may not be true. So the first assumption is actually about the residuals. It is assuming the residuals follow a normal distribution. The way it's set up, that the mean of that distribution is going to be 0. You have some above, some below. You minimize the sum of squared errors, you're going to have the mean being 0. But there's no guarantee that it's actually going to be normally distributed around that value. So the first assumption is that really the sum of squared errors, the process for getting the best line, only really works if the errors are normally distributed. That may not be the case. There can be other things that come up with the errors, the residuals, which is a way to check basically the next assumption. It assumes their observations are independent of each other. Okay, we saw with spatial autocorrelation, when I had said, what are the implications of spatial autocorrelation? That was one of those videos. The implication is that it means our observations are not truly independent of one another. That is an assumption here within regression. It also assumes that the residuals are independent of each other, such that if I make a mistake with predicting Mon County, I should not be making an equivalent mistake for predicting Preston County just because they're neighbors. What we can do to check this, there are ways to check this, which will show up in kind of the output for when we do regression in ArcGIS. This one we'll be doing ourselves. And this sets up some of the ideas going into next week, really, where you'll see doing this. Where we'll run Moran's eye, run a test of spatial autocorrelation on the residuals, not the input values, but the residuals, to see if those errors are independent of each other, at least from a geographic or spatial perspective. Another assumption bigger x values do not mean bigger or smaller errors. So, okay, what might this look like? I'll draw the idea in a very small scatter plot here. So we have our scatter plot, we have our regression line. And it kind of looks like a cone, where small values of x, the points are closer to the line. Big values of x, the points are farther away from the line. If your scatter plot looks like that, you have a problem. You're not meeting the assumptions of this linear regression. And in a way, this kind of leads to probably the last major pitfall or assumption where regression can go wrong. It assumes a linear relationship. So if I have a relationship that looks more like kind of like x squared, and there's a very clear curve there, that's not a linear relationship. Trying to fit a line to this is not going to work too well. There are ways around that to basically try to use something other than a line to fit into this. But if you're just putting in x against y, you're going to have errors because that is not a linear relationship. And trying to fit a line to this is going to make it look like there's a worse relationship than there actually is. Those are the main assumptions that underlie regression, and if those assumptions are not met, you may not be able to trust your results. And throughout, basically what it is saying is, there may be a relationship between those two variables that you're not able to see because the assumptions are not met. So consistently, it would basically lead you to accept the null hypothesis when maybe you're not necessarily wanting to do that. The last pitfall is not related to the assumptions, but is related to correctly interpreting values that you get. Is that r squared and p, in a sense, go in opposite directions. They both are on the interval between 0 and 1. But if you have a relationship, your p-value is going to be low. But you have good predictions. R squared is going to be high. And P is going to say the null hypothesis, probably not true. It's low. If there isn't a relationship, the p-value is going to tell you, yeah, you should probably accept the null hypothesis. It's going to be higher. But that R squared value is going to be low. It's going to be close to 0 because you don't have good predictions. So those are the pitfalls for interpreting our regression between the different assumptions here and correctly understanding R squared versus P in seeing and working with the outputs that you get from, whether you get it from ArcGIS, from Geoda, or other software systems. So as always, if you have questions, please, by all means, feel free to send an email, to speak up in class, and thank you for watching. I'll see you at the next video.